What is concurrency? Programs do not always run one step at a time. Sometimes multiple things happen at once. A web server handles many users. A phone plays music while you browse. This is concurrency. Today we understand what concurrency means and why it matters. Most code executes sequentially. One instruction finishes, the next begins, step by step, in order. This is simple to understand. You read code top to bottom. That is the order things happen. Sequential execution is predictable. Given the same input, you get the same sequence of events, but sequential has limits. If task A takes 5 seconds and task B takes 3 seconds, running them sequentially takes 8 seconds. You must wait. What if task A is waiting for network response? The CPU sits idle while waiting. Wasted potential. Concurrency means multiple tasks make progress in overlapping time. Task A starts. Before it finishes, task B starts. Both are in progress. They might switch back and forth, or they might run truly simultaneously. Concurrency does not mean simultaneous. It means overlapping. While A is for network, B can run. When B waits for disk, A can resume. This is like cooking dinner. When B waits for disk, A can resume. This is like cooking dinner. You do not wait for water to boil before preparing vegetables. You start the water, then prepare vegetables while waiting. Multiple tasks, overlapping progress. Concurrency is about dealing with multiple things at once, not necessarily doing them at once. These terms are related but different. Concurrency is about structure, organizing a program to handle multiple tasks that can be in progress. Parallelism is about execution, actually running multiple computations at the same instant on multiple processors. Concurrency is possible on a single CPU. The processor switches between tasks. Only one runs at any instant, but many make progress over time. Parallelism requires multiple CPUs or cores. Multiple instructions truly execute simultaneously. All parallel programs are concurrent. Not all concurrent programs are parallel. A web server can be concurrent even on one core. It handles many connections by switching between them. Add more cores and it becomes parallel too. Responsiveness. A user interface must respond even while background work happens. Without concurrency, the UI freezes during computation. With concurrency, computation happens alongside user interaction, throughput. A server can handle more requests if it does not wait for each to complete. While one request waits for database, another request gets processed. Resource utilization. CPUs are fast. Networks and disks are slow. If you wait for I/O, the CPU idles. Concurrency keeps the CPU busy while waiting for I/O elsewhere. Real-world modeling, the world is concurrent. Users, sensors, services act independently. Concurrent programs model this naturally. Concurrency enables systems that scale, respond, and efficiently use resources. Concurrency is hard. Non-determinism, the order of operations across concurrent tasks is not fixed. Run the same program twice, get different orderings. Debugging becomes difficult. Race conditions. Two tasks access the same data. The result depends on who gets there first. Bugs that appear and disappear randomly. Coordination. Tasks sometimes wait for each other. Task B needs the result of task A. Managing this coordination is tricky. Reasoning. Sequential code is one story. Concurrent code is multiple interleaved stories. Your brain must track all possibilities. These problems are not insurmountable, but they require new thinking. You must design for concurrency, not bolt it on. Think of concurrent execution as interleaving. Task A has steps A1, A2, A3. Task B has steps B1, B2, B3. Possible orderings A1, A2, A3, B1, B2, B3, or A1, B1, A2, B3, or BAM's rump A1, A2, B3, B4 to believing, or BAM's wrong correctly for all of them. This is the fundamental challenge. You cannot assume a specific ordering. You must handle any ordering. When a specific ordering is required, you must enforce it explicitly. Otherwise, the system chooses freely. Another way to think: multiple timelines. Each concurrent task is its own timeline. Events happen along each timeline. Where timelines interact, coordination is needed. Sequential code is one timeline, easy to follow. Concurrent code is multiple timelines, easy to follow. Concurrent code is multiple timelines that occasionally merge. When they merge, whose version wins? What happens if they conflicted? Time goes left to right. Each task is a horizontal line. Interactions are vertical connections. When timelines touch, problems can occur. Keeping timelines independent is safer. When they must touch, do so carefully. Concurrency affects how you write code. Shared state becomes dangerous. If two tasks read and write the same variable, chaos ensues. You must protect shared state or avoid it. Testing is harder. You cannot easily reproduce bugs that depend on timing. Tests might pass 99 times and fail once. Logging helps. When things go wrong, logs show what happened and when. Include timestamps and task identifiers. Design matters more. Poor concurrent design leads to bugs that are hard to find and fix. Good design prevents problems before they occur. Let us summarize. Sequential execution is simple but limited. One thing at a time. Concurrent execution is multiple tasks making progress in overlapping time. Concurrency is about structure. Parallelism is about simultaneous execution. Concurrency enables responsiveness, throughput, and resource utilization. Concurrency introduces complexity, non-determinism, race conditions, coordination. Think of concurrent execution as interleaving or multiple timelines. Concurrency requires careful design. The payoff is systems that scale and respond. Threads. Concurrency needs a mechanism, something that executes code independently. On most systems, that mechanism is threads. Today we understand what threads are and how they work. A thread is a sequence of instructions that can execute independently. Your program starts with one thread, the main thread. This thread executes your code from the beginning. You can create additional threads. Each thread has its own instruction pointer. It knows where it is in the code. Each thread executes its own sequence of instructions. Multiple threads can run concurrently. While one thread waits, another runs. On multiple cores, multiple threads can run simultaneously. Think of threads as workers. Each worker follows instructions. Multiple workers can work at the same time on different tasks. In Kotlin and Java, you create a thread by providing code to execute. Val thread equals thread with a lambda printing hello from thread. The code inside the braces runs in the new thread. Call thread.start to begin execution. The thread runs concurrently with your main thread. You can also use the thread builder, thread with a lambda printing hello. This creates and starts the thread in one step. When you create a thread, you define what work it will do. When you start it, that work begins executing. A thread goes through states. New, the thread is created but not yet started. Runnable, the thread is ready to run. It might be running or waiting for CPU time. Blocked or waiting, the thread is waiting for something. A lock I/O completion or a sleep duration. Terminated, the thread is waiting for something. A lock I/O completion or a sleep duration. Terminated, the thread has finished its work. It cannot be restarted. You cannot be To do similar work, create a new thread. The lifecycle matters because you interact with threads at different states. Join waits for termination. Interrupt signals a waiting thread. Often you need to wait for a thread to finish. Thread.join blocks the current thread until the target thread completes. Start 3 threads. Call join on each. Your main thread waits for all 3 to finish. This is coordination. The main thread waits for all 3 to finish. This is coordination. The main thread cannot proceed until background work is done. You can join with a timeout thread.join. If the thread is still running, join returns anyway. Join is how you synchronize completion. One thread waits for another. All threads in a process share the same memory. One thread creates a variable. Another thread can read and write it. This is powerful. Threads communicate through shared data. No need to copy or send messages. This is also dangerous. Two threads writing the same variable can corrupt it. Two threads reading and writing can soak in inconsistent values. Shared memory is the source of most concurrency bugs. Race conditions happen because threads share state. Understanding this is crucial. Threads do not have isolated memory. Everything is shared unless you are careful. Sometimes you want data that is not shared. Thread local storage gives each thread its own copy of a variable. In Kotlin, val thread local equals thread local of int. Each thread can set and get its own value. Thread local is useful for context that should not leak between threads. Transaction IDs, user sessions, request context, use thread local when sharing would cause problems. Threads are not free. Memory, each thread needs a stack. Typically hundreds of kilobytes to a few megabytes. 1,000 threads means gigabytes of memory just for stacks. Creation time, starting a thread takes time. The OS allocates resources, sets up the stack. Creating thousands quickly is slow. Context switching, when the CPU switches between threads, it saves and restores state. Too many threads means too much switching overhead. Because of these costs, you cannot have millions of threads. Hundreds to thousands is typical. Thread pools help reuse threads instead of creating new ones, but the fundamental cost remains. Use threads for CPU-bound parallel work. Split computation across cores. Use threads for blocking I/O. One thread can wait for network while others work. Do not use threads for everything. They are heavy. For massive concurrency, lighter abstractions exist. Threads are the foundation. Higher level tools like Coroutines are built on threads. Understanding threads helps you understand everything built on them. Let us summarize. A thread is an independent sequence of execution. Create with thread with code block and start with start method. Threads go through lifecycle: new, runnable, waiting, terminated. Use join to wait for completion. Threads share memory. This enables communication but causes problems. Threads have costs: memory, creation time, context switching that cause problems. Threads have costs. Threads are the fundamental concurrency mechanism. Know them well. Shared state problems. Threads share memory. This seems useful, but it is the source of the hardest bugs in concurrent programming. Today we understand what goes wrong when threads share mutable state without protection. When multiple threads access the same data and at least one writes, problems occur. Read-only sharing is safe. 10 threads reading the same value see the same thing, but if one thread writes while another reads or writes, chaos ensues. The reader might see partial writes. Two writers might overwrite each other. This is not a bug in your logic. Your code might be perfect for sequential execution, but concurrent execution changes everything. The same code that works sequentially can fail concurrently. This is subtle. This is dangerous. A race condition is when the result depends on the timing of operations. Two threads increment a counter. The final value should be 2, but sometimes it is 1. Who wins the race to read, modify, write? Race conditions are non-deterministic. Run the program 10 times, get different results. The bug appears sometimes, not always. Race conditions are hard to reproduce. The timing that triggers the bug might be rare. Tests pass 999 times, fail once. Race conditions are hard to debug. By the time you add logging, the timing changes, the bug disappears. A dida race is a specific kind of race condition. One thread writes a variable while another thread reads or writes it without synchronization. Data races cause undefined behavior. The reading thread might see partial writes, it might see old values, it might see corrupted data. A race condition is about logic depending on timing. A data race is about memory access without coordination. All data races are race conditions. Not all race conditions are data races. Preventing data races is the first step to correct concurrent code. Many operations that look like one step are actually multiple steps. Count looks atomic. It is not. It reads count, adds 1, writes count, 3 steps. If two threads do count simultaneously, both might read the same value, both add 1, both write. You wanted 2, you got 1. This is called a lost update. One update is lost because the other did not see it. Even simple operations are not atomic. Assigning a long on some platforms is 2 writes. The reader might see half of each value. Never assume an operation is atomic. Check the documentation. Use atomic types when needed. When one thread writes, do other threads see the write? CPUs have caches. A thread might write to its cache. Other threads read from their caches. They do not see the update. This is a visibility problem. The write happened. It is just not visible. Without proper synchronization, a thread might never see updates from another thread. It might read stale data forever. A common pattern, a flag to stop a loop, done equals true in one thread. Why not done in another? Without visibility guarantees, the loop might never see done become true. Visibility requires synchronization. Just because you wrote a value does not mean others see it. Compilers and CPUs. Reorder operations for performance. You write A equals 1 semicolon B equals 2. The CPU might execute B equals 2 semicolon A equals 1. For a single thread, this is fine. But another thread might see B equals 2 before A equals 1. It expects if B is 2, A is 1, but A is still 0. Logic breaks. Reordering is invisible in single-threaded code. It becomes visible in multi-threaded code. Synchronization prevents harmful reordering. Without it, you cannot assume operations happen in the order you wrote them. Unsynchronized concurrent access is unpredictable. It might work perfectly on your machine. It might fail on another machine with different timing. It might work under light load. It might fail under heavy load when timing changes. It might work with one JVM. It might fail with another that optimizes differently. You cannot test your way to correctness. A passing test does not prove absence of race conditions. You must reason about all possible interleavings. You must design for correctness, not just hope. Signs of shared state problems, inconsistent results. The same operation gives different outcomes. Corruption. Data structures end up in impossible states. Deadlocks. The program freezes. Threads wait for each other forever. Rare failures. Bugs that happen occasionally. Impossible to reproduce. If you see these symptoms in concurrent code, suspect shared state problems. Check every variable that multiple threads access. Let us summarize. Shared mutable state plus concurrent access equals problems. Race conditions results depend on timing. Data races, unsynchronized reads and writes. Non-atomic operations, compound steps can interleave. Visibility, writes may not be seen by other threads. Reordering, operations may not execute in written order. These problems are subtle, unpredictable, and hard to debug. Next, we learn how to prevent them. Synchronization. We have seen what goes wrong with shared mutable state. Now we learn how to prevent it. Synchronization is the art of coordinating access to shared data. Today we understand the fundamental tools, locks, volatile, and atomic operations. The core idea is mutual exclusion. At most, one thread accesses the protected code at a time. If two threads want to enter the critical section, one waits, the other executes. When done, the waiting thread can proceed. This eliminates race conditions in the protected section. Only one thread touches the data at once. No interleaving. Mutual exclusion is the foundation. Locks implement it. Synchronized blocks use it. The cost is waiting. Threads that could run in parallel must wait for each other. Concurrency is reduced to protect correctness. A lock is an object that enforces mutual exclusion. Lock.lock acquires the lock. If another thread holds it, wait. If free, take it. Inside, you access shared data safely. Only you have the lock. Lock.unlock releases the lock. Another waiting thread can proceed. Always unlock if you forget. Other threads wait forever. Use try finally to ensure unlock even if exceptions occur. In Kotlin and Java, you can use reentrant lock or synchronized blocks. A synchronized block is a simpler way to lock. Synchronized parenthesis object close parenthesis brace code close brace. The object is the lock. Only one thread can be in synchronized blocks on the same object. Every object in Kotlin and Java can be a lock. You choose what to synchronize on. Synchronized blocks automatically unlock when exiting. Even on exception, no try finally needed. In Kotlin, asynchronized on a method synchronizes on this for instance methods. Synchronized blocks are convenient but lock the entire block. Fine-grained locking requires explicit locks. Synchronization provides three guarantees. Mutual exclusion, only one thread in the protected section. Visibility, changes made by one thread are visible to the next thread that acquires the lock. No stale data. Ordering, operations before releasing the lock happen before operations after acquiring it. No harmful reordering. These three together ensure correct behavior. The lock is not just about one at a time. It is about seeing and ordering. Without the lock, you have none of these guarantees. Deadlocks occur when threads wait for each other in a cycle. Thread A holds lock 1, wants lock 2. Thread B holds lock 2, wants lock 1. Neither can proceed. The program freezes. Deadlocks happen when acquiring multiple locks in different orders. Then B versus B, then A. Preventing deadlocks, always acquire locks in the same order. If everyone takes lock 1 before lock 2, no cycle forms. Detecting deadlocks, the JVM can detect them. Thread dumps show which threads wait for what. Deadlocks do not crash, they freeze. The symptom is a program that stops doing anything. No errors, no progress. Sometimes you do not need mutual exclusion, you just need visibility. Volatile marks a variable for special treatment. Reads and writes go to main memory, not caches. A write to a volatile variable is immediately visible to all threads. No stale data. Volatile also prevents reordering around the variable. Volatile is enough for flags var done by volatile equals false. One thread writes, another reads. No race because there is no compound operation. Volatile is not enough for conda++. That is red modify write, not atomic. Use atomic types instead. Atomic operations complete in one indivisible step. Atomic integer provides atomic increment. Counter.increment and get. Atomic operations provides atomic object updates. Atomic use special CPU instructions. No locking needed. Very fast. Compare and swap. Change the value only if it equals the expected value. If another thread changed it first, retry. Atomics are great for counters, flags, and simple state. For complex state with multiple variables, locks are often clearer. For simple flags and visibility, volatile. For counters and simple state, atomic types. For protecting complex operations on shared data, synchronized or locks, use the simplest tool that works. Volatile if visibility is enough. Atomics if you need atomic updates. Locks when you need mutual exclusion over multiple operations. More complexity means more chances for bugs. Keep synchronization as simple as the problem requires. The best solution is often avoiding shared mutable state entirely. Immutable data needs no synchronization. Let us summarize. Mutual exclusion, one thread at a time in critical sections. Locks and synchronized enforce mutual exclusion, provide visibility and ordering. deadlocks, circular waiting for locks, prevent by consistent ordering, volatile visibility without mutual exclusion, for simple flags, atomic types, indivisible operations, for counters and simple state. Choose the right tool. Keep it simple. Prefer avoiding shared mutable state. Synchronization makes concurrent code correct but requires careful design. Introduction to coroutines. Threads work, but they are heavy. What if we could have the benefits of concurrency without the cost? Kotlin Coroutines offer exactly this. Lightweight concurrency that scales. Today we meet coroutines and understand what makes them different. Threads are expensive. Each thread needs a stack. Context switching has overhead. If you have thousands of concurrent tasks, thousands of threads consume gigabytes of memory. The system slows down. Blocking is wasteful. A thread waiting for network does nothing. It holds resources while idle. Modern applications need more concurrency than threads can provide efficiently. Web servers handle thousands of connections. Mobile apps perform many background operations. We need something lighter. A coroutine is a suspendable computation. Like a thread, it executes a sequence of code. Unlike a thread, it can suspend without blocking the underlying thread. When a coroutine suspends, the thread is free. It can run other coroutines. When the suspension ends, the coroutine resumes, possibly on a different thread. Coroutines are cheap. Thousands, even millions, cost little. On a different thread. Coroutines are cheap. Thousands, even millions. You can have a coroutine per request, per user action, per concurrent operation. Think of coroutines as lightweight threads, but technically they are different. They cooperate rather than being preempted. Threads are OS managed. The OS schedules them. The OS context switches them. Coroutines are library managed. Kotlin's coroutine library suspends and resumes them. No OS involvement for suspension. Threads block. When a thread waits, it holds the thread. The thread cannot do other work. Coroutines suspend. When a coroutine waits, the thread runs other coroutines. When a thread runs released, this is the key difference. Suspending releases resources. Blocking holds them. You can have millions of coroutines on a few threads. You cannot have millions of threads. Blocking ties up a thread. Thread.sleep blocks. The thread does nothing. Suspending frees the thread. Delay suspends. The coroutine waits, but the thread works. This matters for scalability. A server with one thread per connection blocks on I/O. With coroutines, one thread handles many connections, suspending while each waits for IOI. Sequential-looking code that does not block. Call a suspend function. Wait for the results, continue. It looks like blocking, but is not. Suspending is cooperative. The coroutine decides when to suspend. It is not preempted like a thread. Launch starts a new coroutine. Launch brace do something close brace. The code in braces runs in a new coroutine. The launch returns immediately. Launch is fire and forget. It starts work but does not return a result. The result of launch is a job. You can use it to cancel or wait for the coroutine. Launch needs a scope. Coroutines do not run in isolation. They belong to a scope that manages their lifecycle. Async starts a coroutine that produces a result. Val deferred equals async brace compute something close brace. The code runs in a coroutine. The result will be available later. To get the result, call await. Val result equals deferred.await. Await suspends until the result is ready. It does not block. Use launch when you do not need a result. Use async when you do. Async plus await is like starting a background computation and collecting its result. Every coroutine runs in a scope. The scope tracks all coroutines launched in it. When the scope ends, its coroutines are cancelled. This is structured concurrency. You cannot launch a coroutine that outlives its scope. No orphan coroutine that outlives its scope. No orphan coroutines. Run blocking creates a scope that blocks until all its coroutines complete. Good for main functions and tests. Coroutine scope creates a scope that suspends until complete. Good for grouping related operations. Scopes prevent leaks. If you forget to wait for a coroutine, the scope handles it. A simple example: run blocking brace, launch delay 1000 print task 1 done, launch delay 500 print task 2 done, print both launched, close brace, print all complete. Run blocking creates a scope. Two coroutines launch. They run concurrently. Task 2 finishes first because its delay is shorter. After both complete, the scope ends, the outer print executes. Sequential looking concurrent execution. Let us summarize. Coroutines are lightweight, suspendable computations. Coroutines suspend without blocking threads. This enables massive concurrency. Launch starts a coroutine without returning a result. Async starts a coroutine that produces a result. Await retrieves it. A coroutine scopes manage lifetime and prevent leaks. Coroutines make concurrent code look sequential while scaling efficiently. Suspend functions. We have seen coroutines and the delay function. But what makes delay special? It is a suspend function. Today we understand what suspend functions are and how they enable non-blocking code. A suspend function is marked with the suspend modifier. Suspend fun, fetch data, string. This function can suspend. It can pause execution without blocking a thread. The suspend modifier is a promise. It says this function might pause. The caller must be prepared for that. Any function can be marked suspend. The modifier does not change what the function does. It changes where and how it can be called. Suspend functions look like regular functions. They have parameters, return values, and bodies. The suspend modifier is the only difference. Suspend functions can only be called from specific places. You can call a suspend function from another suspend function. This is natural. If your function calls something that might suspend, your function must also be able to suspend. You can call a suspend function from a coroutine. Coroutines are designed to handle suspension. They know how to pause and resume. You cannot call a suspend function from a regular function. A regular function cannot pause. It has no mechanism for suspension. The compiler enforces this. Try to call a suspend function from main and you get an error. The code will not compile. When a suspend function suspends, the thread is free. Consider delay. When you call delay 1000, the coroutine pauses for 1 second, but the thread does not sleep. The thread can run other coroutines. This is the key insight. Suspension releases the thread. Blocking holds the thread. A suspend function like delay works with the coroutine runtime. It says, "Wake me later." The runtime schedules the wake up. The thread moves on. Compared to thread.sleep, the thread does nothing, it just waits. Wasteful. Suspend functions enable efficient waiting. The coroutine waits. The thread works. You can write your own suspend functions. Suspend fund fetch user ID int user. Inside you call other suspend functions. Maybe a network call that suspends, maybe a database query that suspends. Your suspend function is just a function. It can have local variables, loops, conditionals, everything works normally. When you call a suspend function inside, your function might suspend at that point. When the call completes, your function continues. You do not manage suspension, you just call suspend functions. The runtime handles the rest. Suspend functions compose sequentially by default. Suspend fun load profile first, calls fetch user, then calls fetch orders, then combines results. Each call happens in order. Fetch user completes, then fetch orders runs, then the combination. This looks like blocking code. First do A, then do B, then do C. But it is not blocking code. First do A, then do B, then do C. But it is not blocking. Each step can suspend without hold. Sequential composition is natural. You write code in order. It executes in order. But suspension makes it efficient. If you want concurrency, you explicitly use async. Without async, calls are sequential. This is easy to understand. except for the modifier. Suspend functions are normal. They can have parameters, suspend fun, fetch URL, string. They can return values, suspend fun compute, int. They can throw exceptions, throw IO exception inside the suspend function. They can be extension functions, suspend fun that refresh. They can have generic types, suspend fun, fetch of, t. Everything you know about functions applies. The suspend modifier just adds the ability to pause. The Coroutine library provides many suspend functions. Delay. Suspends for a time. It does not block. Await suspends until a deferred completes. Join suspends until a job completes. With context suspends while switching to a different dispatcher. Yield suspends to give other coroutines a chance to run. Network libraries provide suspend functions for HTTP calls. Database libraries provide suspend functions for queries. The ecosystem builds on suspend functions. Write operations that might wait as suspend functions. Network calls wait for responses. Make them suspend functions. Database queries wait for results. Make them suspend functions. File reads wait for disk. Make them suspend functions. User input waits for interaction. Make them suspend functions. If something might wait, make it suspend. This enables efficient handling without blocking threads. Let us summarize. Suspend functions are marked with the suspend modifier. They can only be called from coroutines or other suspend functions. When they suspend, the thread is free to do other work. Suspend functions compose sequentially by default. Otherwise, they are regular functions with all normal capabilities. Suspend functions are the building blocks of non-blocking code. Coroutine context and dispatchers. Where do coroutines run? How do you control which thread executes your code? Today we explore coroutine context and dispatchers, the mechanisms that configure and schedule coroutines. Every coroutine has a context. Coroutine context is a set of elements that configure the coroutine. It carries information about how the coroutine should behave. Think of context as coroutine metadata. It answers questions like, what thread should this run on? What happens when it fails? What is its name? Context is immutable. You do not modify a context. You create new context by combining elements. The context travels with the coroutine. When you launch a child coroutine, it inherits context from its parent. Context contains multiple elements, each with a purpose. Dispatcher determines which thread or threads run the coroutine. Job tracks the coroutine's lifecycle and enables cancellation. Coroutine name gives the coroutine a name for debugging. Coroutine exception handlers uncaught exceptions. Each element has a key. You access elements by key, context bracket, job close bracket. Elements combine with plus. Dispatchers.io plus coroutine name of worker creates a context with both. A dispatcher controls where coroutines execute. Dispatchers.main runs coroutines on the main thread. Use this for UI updates in Android. Only one thread, so work must be quick. Dispatchers.io is optimized for I/O operations. Network calls, file reads, database queries. Network calls, file reads, database queries. Uses a shared pool of threads that can grow. Dispatchers.fault is for CPU-intensive work. Parsing, sorting, complex calculations. Uses a pool size to CPU cores. Each dispatcher is designed for specific work. Choose the right one for your task. Specify a dispatcher when launching a coroutine. Launch dispatchers.io runs the block on an IO thread. Async dispatchers.fault runs computation on the default dispatcher. If you do not specify, the coroutine inherits the dispatcher from its scope. Run blocking uses the current thread as its dispatcher. Launch inside run blocking inherits this. Most coroutine builders accept a context parameter. The dispatcher is part of that context. Sometimes you need to change dispatchers mid-coroutine. With context switches the context for a block of code. With context dispatchers.io brace block close brace. The block runs on IO, then execution returns to the previous dispatcher. Use this pattern. Start on main for UI, switch to IO for network, switch back to main to update UI with context is a suspend function. It suspends in the current context, resumes in the new context. This is cleaner than launching separate coroutines. Your code stays sequential, but parts run on different dispatchers. Child coroutines inherit context from their parent. When you call launch inside a coroutine, the new coroutine gets the parent's context. Same dispatcher, same job tree. You can override specific elements. Launch dispatchers.io inside the main coroutine runs the child on IO, but other context elements, still inheritance, follows addition rules. Child context equals parent context plus any elements you specify. Specified elements override inherited ones. This makes code cleaner. Set the context once at the top level. Children inherit without repetition. Job is a context element that represents the coroutine's lifecycle. Every coroutine has a job. The job tracks whether the coroutine is active, completed, or cancelled. Jobs form a hierarchy. A parent job has child jobs. When you cancel the parent, all children cancel. You can access the job from context, coroutine context bracket. Job enables structured concurrency. Parent-child relationships are tracked through jobs in the context. Access current context with coroutine context inside the suspend function. Val current dispatcher equals coroutine context bracket continuation interceptor close bracket. Build context by adding elements. Val my context equals dispatchers.io plus coroutine name of worker. Context combine context 1 plus context 2. If both have the same element type, the right side wins. Empty coroutine context is the identity. Adding it changes nothing. Keep context building simple. Usually you just specify a dispatcher and maybe a name. Let us summarize. Coroutine context configures how a coroutine runs. Dispatchers determine which threads execute the coroutine. Main for UI, IO for input-output, default for CPU work. With context switches dispatchers within a coroutine. Child coroutines inherit context from parents. Job is the context element that enables structured concurrency. Choose your dispatcher wisely. The right dispatcher makes your code efficient. Structured concurrency. Coroutines can launch other coroutines. But what happens when things go wrong? Who cleans up? Today we understand structured concurrency, the principle that makes concurrent code manageable and safe. Without structure, concurrency becomes chaos. A function launches a background task. The function returns. The task keeps running. Who tracks it? Who cancels it when no longer needed? Unstructured concurrency leads to leaks. Tasks run forever. Resources stay allocated. Memory grows. Unstructured concurrency leads to confusion. You do not know what is running. You cannot reason about the system state. We need structure. We need clear relationships. We need automatic cleanup. In structured concurrency, coroutines form a hierarchy. When a coroutine launches another, they become parent and child. The parent knows about the child. The relationship is explicit. A scope is the parent. All coroutines launched in a scope are its children. The scope tracks them. This hierarchy is automatic. When you call launch or async inside a coroutine, the new coroutine becomes a child of the current one. The hierarchy enables management. Cancel the parent, children cancel. Parent waits for children, no orphans. A scope determines how long coroutines live. The scope completes only when all its children complete. Run blocking does not return until all launched coroutines finish. The scope cancels when cancelled. All children cancel with it. This is the contract. Children cannot outlive their parent scope. When the scope ends, children end. This prevents leaks. You cannot forget about the coroutine. The scope remembers and ensures cleanup. Cancellation flows down the hierarchy. Cancel a parent, all descendants cancel. Cancel a scope, all its coroutines cancel. This is intentional. If a parent is cancelled, its work is no longer needed. Children doing work for the parents should also stop. Cancellation is cooperative. A cancellation is cooperative. A cancel coroutine does not stop immediately. It stops at the next suspension point if checking for cancellation. Well-written suspend functions check for cancellation. Delay checks. Network calls check. Your long computations should check. Failure also propagates, but differently. If a child fails with an exception, the failure propagates up. The parent is notified. The parent cancels other children. The parent fails. This is called failure propagation. One failure brings down the whole tree. Why? Because children typically do related work. If one part fails, the whole operation is likely compromised. Better to fail fast than continue with partial results. This is the default behavior. Failure goes up, cancellation goes down. Coroutine scope creates a scope that follows structured concurrency. It suspends until all children complete. It propagates failures. It cancels children if cancelled. Use coroutine scope to group related operations. Launch multiple coroutines inside. They complete together or fail together. Coroutine scope is a suspend function. The calling coroutine suspends until the scope completes. This is different from run blocking. Run blocking blocks the thread. Coroutine scope suspends the coroutine. Sometimes you want children to fail independently. Supervisor scope creates a scope where child failures do not propagate up or cancel siblings. One child fails, others continue. The supervisor scope does not fail. You handle failures individually. Use this when children are independent. Processing multiple items where one failure should not stop the others. Multiple network calls where partial success is acceptable. Supervisor scope still waits for all children. It still cancels children when the scope is cancelled. But failure does not propagate. Always launch coroutines in a scope. In Android, use viewModel scope or lifecycle scope. They cancel when the viewModel or lifecycle ends. In libraries, accept a scope from the caller. Let them control the lifetime. In tests, use runTest, which provides a test scope. Never launch coroutines into the void. Always have a scope, always have a parent. This discipline makes concurrent code predictable and safe. Let us summarize. Structured concurrency creates parent-child relationships between coroutines. The scope defines the lifetime. Children cannot outlive this scope. Cancellation propagates down. Cancel a parent, children cancel. Failure propagates up. A child failure cancels siblings and fails the parent. Coroutine scope groups operations with shared fate. Supervisor scope allows independent child failures. Structure makes concurrency manageable. Channels. Coroutines often need to communicate. One produces data, another consumes it. How do they pass data safely? Channels provide a way for coroutines to send and receive values. Today we learn how channels work. A channel is a queue for coroutine communication. Think of a channel like a pipe. One end sends values in. The other end receives values out. The channel sits between sender and receiver. Channels are similar to blocking queue from Java, but designed for coroutines. Instead of blocking threads, they suspend coroutines. One coroutine sends data to the channel. Another coroutine receives data from the channel. They do not need to know about each other. The channel is the intermediary. This decouples producers from consumers. They communicate through the channel, not directly. Send puts a value into the channel. Channel.sendValue. This suspends if the channel is full. The coroutine waits until there is room. Receive takes a value from the channel. Value equals channel.receive. This suspends if the channel is empty. The coroutine waits until a value arrives. Both operations are suspend functions. They pause the coroutine, not the thread. Send and receive can happen in different coroutines. One sends, another receives. The channel coordinates them. Create a channel with channel constructor. Val channel equals channel of int round brackets. This creates a channel that passes integers. Channels are generic. Channel of string passes strings. Channel of user passes users. The constructor takes an optional capacity parameter. This determines how many values the channel can hold. By default, channels have no buffer. Send suspends immediately until someone receives. Rendezvous channel has zero capacity. Channel of T-round brackets. Send suspends until receive happens. Receive suspends until send happens. They meet at the channel. Buffered channel has fixed capacity. Channel of T capacity equals 10. Send only suspends when buffer is full. Receive only suspends when buffer is empty. Unlimited channel has infinite capacity. Channel of T1 limited. Send never suspends. Use queue up. Be careful with memory. Conflated channel keeps only the latest value. Channel of T conflated. Send never suspends. Old values are dropped if not received. Choose the type based on your needs. Rendezvous for tight synchronization. Buffered for some decoupling. Unlimited or conflated for special cases. A channel can be closed. Channel.close round brackets. After closing, no more values can be sent. Receivers can check if the channel is closed. Receive throws closed receive channel exception on a closed empty channel. Better use receive catching or check is closed for receive. Closing signals completion. The producer says, I am done. Receivers finish processing remaining values and stop. Always close channels when done. This prevents receivers from waiting forever. You can iterate over a channel with a for loop. For value in channel brace block close brace, the loop receives values until the channel closes. This is the cleanest way to consume a channel. No manual receive calls. No check-in for closed. The loop suspends when the channel is empty. It resumes when a value arrives. It exits when the channel closes. Under the hood, the for loop uses the channel's iterator. Each iteration calls receive. Close the channel to end the loop. Without closing, the loop waits forever. A common pattern, one coroutine produces, another consumes. Launch a coroutine that sends values, then closes the channel. The producer owns the channel. It creates values, sends them, and signals completion by closing. The consumer iterates over the channel. It processes each value until the channel closes. This pattern is clean and safe. The producer controls the lifecycle. The consumer just processes. Multiple consumers can receive from one channel. Each value goes to one consumer. This enables work distribution. Consider processing a stream of events. A producer coroutine fetches events from a source. It sends each event to a channel. A consumer coroutine receives events. It processes each one. The channel buffers events if the consumer is slow. The producer can stay ahead. When the source is exhausted, the producer closes the channel. The consumer finishes remaining events and completes. This decouples fetching from processing. Each can run at its own pace. Let us summarize. Channels are concurrent queues for coroutine communication. Send puts values in, receive takes values out. Both suspend when needed. Channel types: rendezvous for tight sync, buffered for flexibility, unlimited or conflated for special needs. Close channels to signal completion. Iterate with for loops for clean consumption. Channels decouple producers from consumers, enabling flexible concurrent patterns. Flow basics. Suspend functions return a single value, but what if you need to return multiple values over time? Flow is Kotlin's solution for asynchronous streams. Today we learn the fundamentals of flow. Sometimes one value is not enough. A function that fetches a single user returns user. But what about a function that fetches users as they arrive, one at a time, over time, over time? You could return a list, but then you wait for all values. What if you want to process each as it comes? You need a stream, a sequence of values emitted over time. Process each value as it arrives. Do not wait for all. Sequences give you multiple values lazily, but they are synchronous. Flow gives you multiple values asynchronously. Flow is a called asynchronous stream. It represents a sequence of values that are computed asynchronously. Values are emitted one at a time, over time. Flow is cold. It does not do anything until you collect it. Each collector gets its own stream of values. Think of flow as an asynchronous sequence. Like sequence, it is lazy. Unlike sequence, it can suspend. Flow works with corout. Emissions can suspend. Collection can suspend. Everything is non-blocking. A cold stream starts fresh for each collector. When you collect a flow, it runs from the beginning. Another collector gets another run. No shared state. Cold streams are like functions. Call the function, get a result. Call again, get another result. Each call is independent. A hot stream runs whether anyone collects or not. Channels are hot. They produce values regardless of receivers. If no one receives, values might be lost. Flow is cold. It waits for collection. No wasted computation. No lost values. Use the flow builder to create a flow. Flow brace emit 1, emit 2, emit 3 close brace. This creates a flow that emits 3 integers. Inside the flow block, call emit to send values. Emit is a suspend function. You can call other suspend functions too. Val numbers equals flow of int brace body close brace. The flow builder returns flow of t. The code inside flow runs when collected. It does not run when you create the flow. Creation is instant. Execution is on collection. Collect starts the flow and receives values. Flow.collect brace value arrow process value close brace. For each emitted value, the lambda runs. Collect is a suspend function. It suspends until the flow completes. Collect is a terminal operator. It ends the flow pipeline and triggers execution. Each collect is independent. Collect twice, the flow runs twice. Called behavior. The collector receives values in order. First emission arrives first. Sequential. By default, flow execution is sequential. One coroutine emits and collects. The emitter emits a value, the collector processes it, then the next emission happens. Emit suspends until the collector finishes processing. This is backpressure. The producer waits for the consumer. You do not need to worry about thread safety. Sequential execution means no concurrent access. If you want concurrency, you explicitly use operators like buffer or flat map merge, but default is simple and safe. Consider fetching pages of data. A flow emits each page as it loads. The collector processes each page immediately. No waiting for all pages. Flow brace for page in 1 to total pages emit fetch page of page close brace. The collector receives pages one by one. It can display each as it arrives. User sees progress immediately. If the collector cancels, the flow stops fetching. No wasted network calls. Cancellation works naturally. Several functions create flows from existing data. Flow of 1, 2, 3 creates a flow of fixed values. List.asFlow converts a collection to a flow. Sequence.asFlow converts a sequence to a flow. These are convenience builders. They wrap existing data in flow semantics. Use them when you have data and want flow operators. Transform, filter, then collect. Let us summarize. Flow is a called asynchronous stream of values. Called means it runs fresh for each collector. No shared state, no lost values. Create flows with the flow builder and emit values inside. Collect flows to receive values. Collect is a terminal operator. Flow is sequential by default. Simple and safe, Flow extends coroutines to handle multiple async values elegantly. Flow operators. A raw flow emits values, but you often need to transform, filter, or combine those values. Flow operators let you build pipelines that process data elegantly. Today we explore the most important flow operators. Flow operators come in two kinds. Intermediate operators transform a flow into another flow. They are lazy. They do not start flow execution. Terminal operators start the flow and produce a result. They trigger execution. Collect is a terminal operator. You chain intermediate operators to build a pipeline. Then a terminal operator runs it. Flow.map transform.filter condition.collect process. Map and filter are intermediate. Collect is terminal. Map transforms each emitted value. Flow.map brace it times 2 close brace. Each value passes through the transformation. Map takes a lambda that receives the emitted value and returns a transformed value. The result is a new flow. The original flow is unchanged. Operators create new flows, they do not modify existing ones. Use map when you need to convert each value. String to int, user to user DTO. Raw data to display format. Filter keeps only values that match a condition. Flow.filter brace it greater than 0 close brace. Only positive values pass through. Filter takes a predicate. True means keep the value. False means drop it. The result is a flow with fewer values. Some values are filtered out. Use filter to remove unwanted values, errors, nulls, items that do not match criteria. Transform gives you full control. Inside transform you call emit yourself. You can emit 0, 1 or multiple values for each input. Flow.transform brace value hour emits value hour, emit value times 2 close brace. Each input produces 2 outputs. Transform is more powerful than map. Map emits exactly 1 value per input. Transform can emit any number. Use transform when you need to expand, flatten, or conditionally emit values. Take limits the number of values. Flow.take 3. Only the first 3 values pass. After that, the flow cancels. Drop skips values. Flow.drop 2. The first 2 values are ignored, the rest pass through. Take last and drop last work from the end. But they must buffer values, so they wait for completion. Use take for pagination or limiting. Use drop to skip headers or initial values. Distinct until changed removes consecutive duplicates. Flow emits 1, 1, 2, 1. After distinct until changed, you get 1, 2, 1. Only consecutive duplicates are removed. The final one is not a duplicate of anything immediately before it. Use this for event streams. User moves mouse many events with same position. You only want when position changes. Combine merges 2 flows. Flow 1.combine flow 2 brace a comma b arrow a plus b close brace. When either flow emits, the lambda runs with the latest values from both. Combine is useful for combining independent data sources. Username flow plus user status flow gives combined user info. The lambda runs whenever either flow emits, using the most recent value from each. Both flows must emit at least once before the first combined value appears. Zip pairs values from 2 flows. Flow1.zip, flow2 brace a comma b arrow, pair a comma b close brace. First from flow1 pairs with first from flow2. Unlike combine, zip waits for matching values. If one flow is faster, it waits for the other. The result has as many values as the shorter flow. Extra values from the longer flow are ignored. Use zip when values have a natural pairing. Request response, question answer. Flat map concat transforms each value into a flow, then concatenates the results. Flow.flatmap concat brace value arrow another flow value close brace. Each value becomes a flow. Those flows are collected in order. Concat means sequential. First inner flow completes, then next inner flow starts. Use flat map concat when order matters. Process each item's subflow completely before moving to the next. Terminal operators consume the flow and produce a result. Collect receives each value. The most common terminal operator, toList, collects all values into a list. Waits for completion. ToSet collects into a set. Removes duplicates, first returns the first value, cancels the flow after. Single returns the only value, throws if 0 or more than 1, reduce combines values, reduce brace a comma value arrow ac plus value close brace. Let us summarize. Intermediate operators transform flows, map, filter, transform, take, drop, distinct, until changed. Combination operators merge flows, combine, zip, flat map, concat. Terminal operators produce results, collect, to list, first, reduce. Operators are lazy until a terminal operator runs the pipeline. Chain operators to build expressive data processing pipelines. Error handling in coroutines. Concurrent code fails. Network calls timeout. Computations throw exceptions. How do you handle errors when coroutines are involved? Today we learn the patterns for error handling in coroutine-based code. Coroutines can throw exceptions just like regular code. An exception in a coroutine propagates up the coroutine hierarchy. Child fails, parent is notified, siblings are cancelled. This is structured concurrency in action. Failure propagates, related work stops. Unhandled exceptions crash the coroutine. In some contexts, they crash the entire scope. In Android, unhandled exceptions on main crash the app. You must handle exceptions. Ignore them and your app fails. The simplest approach, try catch. Wrap the code that might fail in a try block. Catch the exception, handle it. Suspend fun, fetch data, try network, call, catch handle error. This works exactly like regular code. Inside a coroutine, try catch works normally. You can catch exceptions from suspend function calls. Be specific about what you catch. Your exception for network errors. Do not catch cancellation exception that breaks cancellation. Try catch is local. It handles errors at the point where they occur. Cancellation exception is special. When a coroutine is cancelled, it throws cancellation exception. This is how cancellation works. If you catch cancellation exception and do not rethrow it, you break cancellation. The coroutine does not cancel properly. Catch E exception, catch a cancellation exception too. Dangerous. Safe pattern. Catch E exception. If E is cancellation exception, throw E else handle. Or be specific. Catch only the exceptions you expect, let others propagate. Coroutine exception handles uncaught exceptions. Val handler equals coroutine exception handler, brace context opa, context exception arrow, log exception, close brace. Added to the coroutine context, launch handler plus dispatches.io brace work close brace. The handler catches exceptions that would otherwise crash. It is a last resort, not a replacement for try catch. Important: coroutine exception handler only works with launch, not async. Async stores exceptions in the deferred. You get them when you call await. Use handlers for logging and cleanup when exceptions escape all try-catch blocks. Async behaves differently from launch. Launch propagates exceptions immediately. Async stores the exception. The exception surfaces when you call await. Await throws the exception. Try val result equals deferred.await catch handle. This is where you catch async errors. If you never call await, the exception may be lost. Always await your async results. You can also check deferred.isFailed without throwing by using getCompleted with checks. By default, child failure cancels siblings. Sometimes you want isolation. Supervisor job changes the behavior. Child failures do not propagate to siblings. Val supervisor equals supervisor job. Use it in your scope. With supervisor job, each child fails independently. One child throws, others continue. Supervisor zob scope creates a scope with this behavior. Children are isolated. Use supervision when children are independent. Processing items in parallel where one failure should not stop others. Flows have their own error handling. The catch operator handles exceptions from upstream. Flow.map might throw.catch brace arrow emit fallback close brace.collect catch receives the exception. You can emit fallback values, you can log, you can rethrow, catch only catches operators before it in the chain. Exceptions in collect are not caught. For collect errors, wrap the entire collect in try catch. On completion runs when the flow completes, successfully or not. Flow.onCompletion brace cause arrow if cause not null log arrow close brace. If there was an exception, cause is not null. If flow completed normally, cause is null. Use onCompletion for cleanup, logging, or UI updates that should happen regardless of success. OnCompletion does not suppress exceptions. They still propagate after onCompletion runs. Let us summarize. Exceptions in coroutines propagate through the hierarchy. Use try-catch for local error handling. Avoid catching cancellation exception. Coroutine exception handlers uncaught exceptions at the scope level. Supervisor job isolates child failures. Flow uses catch for upstream errors and onCompletion for cleanup. Handle errors deliberately. Unhandled exceptions crash your application.